Vous avez repris assez Fawaz les cours ديالكم
Oui.
Les cours ont commencé ديال S3 S5
حنا بدينا حنايا. انا العام اللي فات ملي كان جا الكوفيد المؤسسه ديالنا ليتابليسمون دابا راني في لو اس تي
داكور.
حتى بلاتفورم ديال هادو غوش
عندكم لي فيكسي غير
وي واحد لا بلاتفورم ديال غوشيرش دايرينها في لانسا و ميم طون كولابوراسيون مع لا فاكولتي دي سيونس. سالينا حنايا ماشي سالينا الحمد لله ضربنا هذاك الشيء كنا ا ديستونس ومع لي زيتيديون مع هذاك الشيء. دابا بدينا ما عنديش هاد السوماتر شويه لي كور عندي غير دي طرافو براتيك انا كنشوف الطريقه كيفاش راني غادي ندير لهم بواحد لا ميثود ندير لهم اونلاين وغادي نمشي نديهم حضوري نسخن.
Keynote. Welcome everybody to this fourth conference on materials and environmental science, which is now virtual conference in this condition of pandemic COVID-19. This international conference is organized by the competition of the University Mohammed I and University King Abdullah in Saudi Arabia, as well as the support of ISMAEL, which is a research institute in solar energy and new energy, and also SAADOUNE, the Moroccan Center for the Development of Science, on the initiative of Professor Hamouti Belkheir, who is present as a gift in the animation of scientific activities and the communication of works between research. And in the theme of this scientific meeting is new materials for sustainable energy development. We know that Moroccan policy is direct toward renewable energies in its various aspects and encourages and supports research in this field. So this is how the scientific manifestations intended as platform for exchange between Moroccan scientists and their colleagues in the world to examine recent research within the framework of the development of new materials to lead to new energy storage production systems. And in this context, allow me to receive online full Professor Dr. ISMAEL SAADOUNE from Qadi Iyad University of Marrakech, Faculty of Science and Technologies. He was graduated from the University of Bordeaux in France, and he had a lot of works in the topic of active materials in lithium-ion batteries. He has a lot of papers. He is very active research in this field, and he has a lot of students, master students, a lot of students in PhD degree. I will now give him, I want to thank him for this presentation, and I will give him the words to present the presentation in lithium and sodium ions batteries as convenient electrochemical energy storage technologies. You have the talk, Mr. ISMAEL SAADOUNE.
Okay. Thank you very much, Mr. Sherman, for this nice presentation, for this nice introduction. Before starting, I would like to thanks my friend Belkheir Hamouti for inviting me to this big conference, and I would like also to thank the Fawad for his support to be there today, direct live in Facebook, in YouTube, and it's a great pleasure for me to present our recent work or just challenges of lithium and sodium-ion batteries for energy storage. So I will try to fit my presentation in 35 minutes because Belkheir sent an email to be strict in 35 minutes, but if I exceeded 35 minutes, please, you can stop me, no problem. So I will start by giving some general context of energy storage problem issue for the development of energy, clean energy, and for electrical vehicles. So, and then I will focus on electrochemical energy storage, namely the batteries. And after that, I will give some challenge of lithium-ion batteries, and I will introduce some recent R&D works done in our lab here in Marrakech in partnership with many colleagues from abroad. And I will finish by talking about beyond lithium-ion battery, and we will focus on sodium-ion battery, which is a new technology that could replace lithium in some application. And I will finish by one slide, just as a conclusion, where I will put some idea to go ahead if you would like to work on this topic. So let me just remind that around 90% of used energy now is non-renewable. Okay, if you see on the left side here, we have some more than about 40% coming from coal, 23% from gas, and so on. So the most used energies are dirt. There are a lot of pollution coming from these sources, because we use this non-renewable energy because they are cheap and they are most popular, because all people know only this type of energy source. But there are two big problems. The first one is that fossil energies are running short. We don't have enough fossil energy to meet our requirement in the future. Secondly, we have a high CO2 footprint of this fossil energy, and we will see this year, for example, or this last 5 to 10 years, the change of climate. And in Morocco, for example, we have this big issue. We have some dry season without many water. So if we look who is using fossil energy and who is polluting our atmosphere, we can see that China is the biggest one. China, India, United States, and Russia and Japan. And there are a proportionality between industrial growth and the gas emission. So we can conclude that developed countries pollute and the others smell their pollution. In Africa, for example, we are not emitting a big quantity of gases, CO2 and so on, but we are smelling, we are just receiving the consequences of this gas pollution. So a new energy consumption model was needed over the world, and especially for African countries. Let me just remind the electricity chain. Normally, all countries, all politics should ensure three things. They should ensure the generation of energy that people need, coming from old source, but also from new source. We need also to deliver this energy to where people need it. So we need the transmission and distribution. You have in Africa, many people living in some islands, some isolated village. So we need to transmit, to distribute this energy where people need it. And we should also store, because we should provide energy when it's needed. So during all this operation, starting from generation, transmission, distribution, consumption, we need in fact to store energy in each steps of this electricity chain. Morocco, by organizing the COP 2020 and so on, Morocco decide to shift from carbon source energies to renewable energy by developing solar and wind, and also by the development of zero emission electric vehicles. We have now some companies like PSA, Peugeot in Kenitra, but we are not so far from Europe, where a lot of companies are now starting to produce electrical vehicles simultaneously with diesel or gasoline vehicles. So we are great need of mobile and stationary energy storage solution. We need to store energy for mobile application, but also for renewable energy, because, as you know, renewable energy are intermittent. We have sun in the day, but in the night we don't have sun. So we should store the excess of energy during the daylight and then use it in the night. So storage, we cannot develop such energies or such vehicles, electrical mobility, without developing energy storage solution. So storage is simply a reversible transformation of the electricity to another form of energy. This is what we teach to our students. There are a lot of storage mechanisms. We have some mechanical energy storage, like pump hydro or flywheels. We have electrical storage, like for capacitor. We have thermal storage, chemical storage via hydrogen, or thermochemical storage. Now, I would like to talk about electrochemical storage, which is a transformation of electrical energy to chemical energy and vice versa. So what is lithium-ion batteries? But first, we started to talk about lithium battery first. Let me just give you a reminder. What is an ideal electrochemical cell? An ideal electrochemical cell is that combine the most electropositive element in the table is lithium, and the most electronegative element of the table is fluor. If we can succeed to have this cell, we could have around 6 volt, which is now the biggest is like 3.7, 4 volt. We can reach almost 6,000 watt-hour per kilogram. It's huge, huge quantity of electricity. But the problem, the fluorine-based chemistry has many drawbacks. We cannot succeed to have these two materials in the same cells because of many chemical drawbacks. Why people are working with lithium? Because lithium can offer very low voltage, okay, as anode material. He can deliver a high capacity, around 4,000 ampere per kilogram. And he's really light, so we can think about mobility. And this is a metal, so the resistivity is very, very low. People are starting to work on lithium battery many years ago, it's in 80s and 70s. And the cell consists of one positive electrode material and lithium foil. Lithium foil is very homogeneous foil. And when starting to charge and decharge, we start to have this evolution of what we call dendritic growth. It's lithium metal growing during cycling, and if it grows, it can short circuit between cathode and anode material, leading to some fire. So people in the 80s leave the lithium batteries until Sony battery that replace lithium here, metal by graphite. So we have lithium only moving from one intercalation material to another intercalation material. There are no lithium metal in the cell. That's why we call it lithium-ion batteries. It's only lithium-ion that moves from one side to other side. To more explain how it works, lithium battery is like all batteries. We have cathode side, anode side. We have two current collector. In the cathode side, we have aluminum. In the anode side, we have copper. And in the current collector, we put our materials here. For example, is lithium cobalt oxide. And in the anode side, we have graphite, for example. And in between, we have electrolytes. So when charging your battery during the night or now, there are movement of lithium from the cathode side to the anode side here. Okay, this is during charge. During discharge, the lithium are coming back to the cathode material. So the quantity of exchanged lithium from one side to the other side give you the capacity of the battery. If you have a huge quantity of lithium moving from one side to the other side, we have a big capacity. And the difference in the potential of two electrodes give you the voltage is proportional to the stored energy. So we need high voltage, we need high capacity. And secondly, we have this reversibility. If the number of lithium moving during charge is equal to the lithium coming back to the during discharge, we have 100% efficiency. Okay, so we need to have this phenomenon reversible for many cycles to get to have a good lithium-ion cell. And you see that during the lithium running, this is a material science challenges inside. We have these cathode materials, interface, electrolyte, and anode material, and so on. So if you would like to charge very rapidly your battery, you should think about what happened inside. Indeed, now many guys are saying that we can charge very fastly our battery. But let me just give you an idea. In electrical vehicles or large-scale energy storage, we have this battery pack. The battery pack is minimum 24 kilowatt hour. It's a lot of modules. So big pack consists of many modules, and each module consists of cells. what I show here is only one set. So you see then, if you would like to have efficient pack, you should have an efficient cell to get it. So the lithium cell, we are trying to perform some cycling in the lab, but when putting in the vehicles, there are a lot of new parameters. So the cell should keep its performance in presence of other cells, a lot of cells around, and also on the embarked electronics, because when you have these vehicles, we have a lot of electronics, battery management system, and the cell should also be used in some extreme condition. So from R&D, we should understand what happens in this poor cell before going to the big pack. So in the labs, for example, I saw in the news that many people are saying we will start to produce battery in Morocco and so on. Let me just remind you, this is not my slide, it's a slide coming from all the companies producing batteries. If you like to start to work on batteries, we have this first step is scientific breakthrough. You should have some idea, make some calculation to produce materials. Secondly, we should synthesize new class of materials. This one can take 2 years just to find the optimum condition or optimum process to produce your materials. And then if you produce it, you have to use it in what we call half cell. Half cell, you use your studied material with lithium metal just in the lab by using some cell developed in the lab. This can take 5 years at minimum. And then we have to go and back to optimize what the cathode side, the anode side, the electrolyte, and so on. And then if you succeeded, you have to prove in the lab scale, in the proof of the concept of the prototype. This also will take a lot of time to transfer what we found in performance in the lab, in the half cell, in the full cell. And after that, you can think about producing batteries. We can think. So from now, if you would like to start now, 1 year ago, and go, if you succeed to have the best material and to produce batteries, you need at least 10 years. So people saying that in the next year or 2 years we'll produce battery, I think they are dreaming. So what is the criteria of the ideal electrode material? You see that the electrode materials are they play the main role of the battery running during charge, discharge, the cathode and the anode, but mainly the cathode. And let me just remind you, when you see the batteries, it's composed from cathode, from the anode, from electrolyte, from the separator, and then you have some extra. The cost of the battery, we have 20% for the cathode, 7% of the anode, and 8% for the electrolyte. So the business is there. And if you see, we see what will happen in the next 10 years. Here we have a graph from showing the application. In 2018, we have the customer, like a laptop or a cellular phone, growing very slowly. But you see here, the electrical mobility will really improve the quantity of battery produced. We predict like 14 times more than what we produce now in 2030. And the right side, we have we have this distribution by countries, and you see that China will for sure will dominate the market, but we have growing of the market of the producer in Europe with the many big consortium now in USA and the rest of the world. But let me give you this very important news that I catch from Giotto last 2 weeks ago. For the first time, in September 2020, the number of registered electrical vehicles here exceed that of diesel. So now the curve is crossing, and we will have much more electrical vehicles in the road than in diesel. And what happened in Europe? Sure, we will arrive to Morocco. Sure, we should be ready to host this technology, but also to survive with. Here from R&D, what what means a good electrode materials, what means ideal electrode materials. The ideal electrode material should have high electronic conductivity because we are transferring electron from the circuit to the chemistry. We should have high conductive material. We should have large particle size for preparing the cathode. We should have a chemically stable material because he should work without interacting with the electrolyte and with the other component of the battery. We should have fast lithium diffusion because if you like to have fast charge or fast discharge, we should have fast diffusion of lithium. And also, of course, we should have low cost and toxicity and also empty crystal site to make easier this insertion. So having this in mind, this is a required condition, but sometimes you have all this condition and your material doesn't work. So we have some limited choice of electrode materials for lithium-ion batteries. I will just present to you this big first challenge. So if you would like to think about materials for lithium-ion battery, there are three approaches. The first one is to select the chemical composition. We have here the periodic table, but when selecting the element, you should think about sustainable development, no toxicity, and abundant element for the cost. So this is the first approach. The second approach is the synthesis process. If you like to produce something, you should think that you would like to transfer to the industry. And if you like to transfer to industry, we should have an energy efficient process. And now people are going to the bio-inspired eco-friendly routes to produce materials. We have many examples. The third process, the third approach is how to use calculation and modeling to predict if your material will present high redox process and high capacity before going to the experimental. This is normally what we should have in the same lab. Guy designing the product, guy designing the process, and many guys or team making some calculation. So if we look, just making calculation here, what means having high energy density? High energy density is the capacity multiplied voltage. So if you would like to have big capacity, big energy density energy storage, you should have a big number of exchanged lithium. You remember, this is give you the heat capacity, or having some high voltage. So if you have these two approach in mind, and if you see what it exists in the literature, we have some low voltage material like tin, carbon, graphite, and so on. They have low voltage, so they are good materials with high capacity. You see here, they are good material for the anode side. But if you see the cathode side, we have oxide here, many oxides. And now if you would like to go to voltage higher than 4.2 volt, we should go to some phosphate and so on. So this is what we call the next step on the bromide cathode for high voltage. And if we have high voltage, we will have high energy density. But if you look also of all these elements here, you will see that they are all made from phosphorus, fluorine, cobalt, manganese, iron, tin, titanium, and so on. And all these raw materials are existing in Africa. And I'm really excited, and as all time I'm advising to people to do not export the raw material like raw, but trying to valorize this African mineral resource as energetic material. Instead of giving iron, we can prepare iron oxide or iron phosphate with highly added value. So let me just remind the technology existing in the market. This is the cell here. For example, you have silicon, aluminum collector, copper collector, you have separator and cathode material. And in general, your cell, your battery is composed from current collector, copper in general, active anode material mixed with carbon and binder. We have electrolyte. We have an active cathode material also mixed with binder and carbon. And you have current collector in the positive side made from aluminum. And here I summarize the existing material and the companies that now the key players of this market. And you will see that both approximately all working here, all companies are in Asia. And you see if I select cathode materials, which is like more than 40 kilo tetrawatt in demand. We have Umicore is Belgium, NCM. We have Sumitomo Metal, LCO, LFP, NCA. What means NCA, LFP, LCO, NCM? Here I give a table. NCM is lithium, nickel, cobalt, manganese oxide with different proportion from nickel, cobalt, and manganese. Of course, the quantity should be equal to 1. So you can see in some cells, NCM111, this means we have equality between nickel, cobalt, and manganese. You have some NCM622, is 0.6 nickel, 0.2 cobalt, and 0.2 manganese, and NCM811. And you see that people now, the technology are going to minimize the content of cobalt. You see here in 1.1, we have 1/3, here 0.2, 0.1, because the cobalt is expensive, and now companies are going to cobalt-free cathode materials. The second example is NCA, which is used by Panasonic and Sony, for example. This is a nickel, cobalt, aluminum. Okay, LMO or LNMO is a spinel made from lithium, nickel, manganese. It's a spinel cathode material. And LFP is lithium iron phosphate. This is the technology that's used in the commercialized batteries. So let me introduce now some works done in such type of electrode materials. Here I have my old papers in 1992 and 1993. When I was a student, I started working on this material in 1989, and the first publication was done in 92. And we published this system, okay, these two systems, and at the same time, Sony launched his first lithium-ion battery in 92. When I started to look in the literature, there are no papers, nothing, only a patent in writing in Japanese. So you cannot understand what happened. Now I understand. Japanese started to think about commercialization of lithium-ion battery. That's why they patented all this composition. But we were scientific in French at that time, and we published. And we published this curve. You have this charge and discharge, very reversibility, high reversibility, even if at that time we didn't have a good cell. We don't have optimization of the cell electrolyte binder or technology of assembly. And at that time, we think about low quantity of cobalt at that time. And this material, what was published in 1992, was used as starting material to prepare NCA, because NCA is that material we remove 5%, 0.5 cobalt and replace it by aluminum. So I'm so happy to see that, but I think at that time we could be rich if we decide to patent instead of publish. We, in our another approach for university, for R&D university, is to correlate the electrochemical performance of this NMC material to their magnetic properties. In the structure, if you see here, you have layered structure with transition metal in the slabs, and you have nickel, cobalt, and manganese. Cobalt is diamagnetic, and nickel and manganese are paramagnetic. So if we can correlate the magnetic properties with the lithium diffusion, because if you have some frustrated ferromagnetic behavior, you have localization, and lithium cannot move very fastly. And here we have this in applied physics paper. We showed that we can moderate, we can optimize the performance here and capacity if we decide how the content of nickel and cobalt, and to how to correlate magnetic properties and energetic performance. The second example that we would like to present is LMO. This is a spinel. So spinel, this LMO spinel is able to deliver high potential, high voltage, 4.7 volt, which is very, very important for power for electrical vehicles. Okay, we can have like 135 milliampere, but the voltage is high, very high. But the problem is this material works very good at room temperature. But if we increase at 60, the properties are worse. Why 60? Because when you are using your battery in vehicles, the vehicles will heat, and you will generate heat, and the temperature of the vehicles or the temperature of your laptop or something like that could increase until 60, and your battery should work good at room temperature, but also he should preserve the performance at higher temperature. So what we do at that time is to replace a small amount of manganese by another element. In here you see we have the performance at 25 degree and 55 degree here. This is cycling properties at 1C, and we have exactly the same properties at higher temperature. And if you see here, 10C, 20C, 30C, 40C, which means if you have 10C, for example, this means that you discharge your battery in 1/10 hour. This means 6 minutes. Discharging battery in 160C means that you are discharging your battery in 1/60 hour. This means 1 minute. And you see we have some preservation. We keep the capacity higher, even we discharge or recharge our battery at fast current. So after that, what we did with Akhlalouche is my old student, who is now a professor at Marrakesh, and he's a graduate from University Mohammed Ier from Oujda, and come to Marrakesh to prepare his PhD. What we do is here we have the half cell. Remember, half cell with our spinel and lithium. You see, we have voltage around 5 volts, and we use one anode materials called LTU. Okay, we have flat voltage at 1.5 volt, and the next step is to build the full cell. So using this one as cathode and this one as anode. And the problem is how to optimize the capacity, how to optimize the weight in the anode and cathode side. And you see that we succeeded to have almost more 1,000 cycles. Is too much from the lab, okay? And we have this voltage profile. So this was also published, unfortunately, in energy technology, but we should have in mind that we can patent our results, but it's too late now. The third example is LFP, type electrode material. LFP is lithium iron phosphate. So if you see here, this lithium iron phosphate is made from PO4 tetrahedra, and you have your iron in octolite site. So this is the discharge curve here. We have a plateau. We have equilibrium between LFP with lithium in blue and without lithium. So here we have material, this one, and here this one. And you see we will compare the capacity of LFP with what we use now in our car. We have 4 times capacity, 4 times autonomy. But the problem of phosphate is their low conductivity. So this material was discovered by Goodenough in 1997, but the problem of this low conductivity was fixed by Hydro-Québec, who patented the process of coating the particle in 2000. And now this makes this company very rich because they are selling this LFP coated in the market. So the theoretical capacity is 170, but he has low electron conductivity, so we need to coat. And all lithium ion can be removed. You see, here is the starting material. We can remove all the lithium. So we have a bigger capacity. In the oxide, for example, we can remove only 50% of lithium. In the case of iron phosphate, we can remove all lithium because the structure is stable of phosphate. But the problem, we have low energy density because we have low voltage. You see 3.2 volt here. And we have low unit cell volume. You see the volume of the cell is very low during charge and discharge process. This means that we will have a good mechanical properties of phosphate. So this is LFP, and I will be back to phosphate later. Second challenge of lithium-ion battery is to understand the mechanism. You see, it's very easy to see that we have lithium moving from one side to other side and then back. But the mechanism is much more complicated. You should understand what happens in the interface between the current collector and the cathode, inside the cathode, between the cathode and the electrolyte, and in the anode side. So we should have it, keep in mind that we need to have some in situ analysis. In situ, that means that we have your cell and we are following the XRD, XPS, SEM, Raman to see what happens in operando in your cell. But in general, there are 3 mechanisms. The first one is a simple lithium insertion. We have a structure, we introduce lithium by some van der Waals bending, and then we remove it. So this means soft chemistry. In France, we said la chimie douce. We have just intercalation of lithium during a discharge and the extraction of lithium without changing the structure. This is soft chemistry. We have the second mechanism, is what we called alloying. So you have this metal like silicon or antimony as anode materials, and we put lithium and we form some alloy, lithium metal. The problem of this mechanism that we have huge volume change during charge and discharge. If you have volume change, big volume change, you can produce some crack in the particle, and then your performance are going down. The third mechanism is what we call the conversion mechanism. You start by some oxide, for example, from some NEO, for example, and then when reaction with lithium, you form new materials, new species. So your starting material convert to new material. That's why we call it conversion. For this mechanism and this mechanism, we have huge capacity, but the problem, we have some life cycle is very reduced comparing to the insertion where we have lower capacity, but we can have a long-term cycling. So coming back to this in situ characterization, we with the Ilham Bizza, who defended in 2016, we started to study this iron manganese. Remember, LFP, we have this problem of low voltage, very low voltage. So we introduced manganese to increase the voltage, and if we increase the voltage, we can increase the energy density. So this material was prepared in the lab in some special condition, and then as phosphate have low electronic conductivity, we use sucrose from the table, from kahwa, okay, from we use it as carbon source to put carbon and to make pyrolysis around the particles. So here you have XRD. This is a job of the chemist, of solid-state chemists. We start by XRD. You understand the structure. You see that we have tunnels of lithium, so we can remove and put lithium very easily and very reversibly. And then here we use Raman spectroscopy to evidence the existence of carbon in this composite. And you see here is the voltage of LFP 3.5, but we try to enhance, now put the voltage as 4 volt, and we have like two processes here. We have two redox processes, one with iron, another with manganese. And to understand what happened, we use in situ XRD to flow up what happened here during cycling in each point of the charge and discharge process. This is was the aim of our collaboration with KIT Germany within some win-win collaboration. We prepare our material in Morocco and we use the facilities inside. And you see here they have some special cell, two cells simultaneously to check the reproducibility during charge and discharge. And you see we follow the charging process and the discharging process in situ, and we try to calculate the unit cell parameter. And you see, normally we should have one phase, maximum 2 phases during charge or discharge. But in some cases, we get 3 phases. So this means that we have some kinetics problem, which is normal in phosphate, where we have low conductivity in the particle size, in the particle of the phosphate. This is really good topics to understand what happened and to design new phosphate with porosity, with particle size, to have only 1 or 2 phases during cycling, during charge or discharge process. The third challenge of lithium-ion battery is electrolyte. Now the electrolyte is the electrochemistry of solution, in fact. The used electrolyte now is LiPF6, dissolved in organic solvent. The problem now, we are trying to have higher capacity in the future, to higher energy density. To get high energy density, we should have higher voltage. But the problem, the existing electrolytes are not stable at high voltage. So what people are doing now is to use some non-flammable solvent, because we have some organic, we can burn. We can use like ionic liquid, for example. We can use some stable lithium salt in order to have higher voltage. We can use some additive, This one is really the focus in electrolyte. And sometimes now people are going to another type of electrolyte using some polymers, some free or based additive or solid state electrolyte. That what Volkswagen is doing now. But if you see in Morocco, for example, there are no obvious R&D activity in Morocco electrolyte. This is the topics what I'm trying to implement in Marrakesh, and we just submit a project to OCP or to the recent OCP call, just to work on electrolyte and then see what happened when the contact between electrolyte and electrode. The number 4 is the safety of this technology. I think you have in mind what happened in 2016, for example, for Tesla, some vehicles here. We have some Samsung Galaxy burning here. We have some laptop burning in 2006. And you see, here's the technology. Is LCO, you remember, LCO is lithium cobalt oxide, NMC, NCA, LCO, NMC. And this means that practically only oxide can produce this problem, this big problem. Just very fastly, what is what causes this safety issue? We can have some external abuse condition like external heating, overcharging, over-discharging, high current charging, or so on. We can have some internal events inside the cell, like electrode-electrode reactivity, some decomposition, or some side reaction. We can have some lithium platinum and internal short circuit. If this phenomenon, and if we are heating, we can get explosion and smoke, leak, and gas venting and flame in the cell, and we can see what happened. So combustion, combustion for the chemists, you need oxygen for doing combustion reaction, or your cell is closed, is sealed. So oxygen is coming from the electrode material, from your oxide. So this is why we have this problem only with oxide here. So now how to action for safety is one, to replace the flammable organic electrolyte by some polymers or solid state electrolyte. This is also good topics for batteries, or replace the oxide cathode material like lithium cobalt oxide with polyanionic material like phosphate, fluorophosphate, or silicate. I have this picture. Why we have this oxygen release? You see, this is your materials. This is schematization. You have your lithium surrounded by oxygen, and this oxygen is common between the lithium and between cobalt, for example. When you are charging your battery, you are oxidizing cobalt to cobalt 4+. So you have big covalency between cobalt 4+ and oxygen, and we have some overlap between cobalt 3p band with oxygen 2p band. This means that during oxidation, we are oxidizing not only cobalt, but also oxygen to generate oxygen gas that contribute to the flammability of your solvent. In the phosphate, for example, we have this oxygen linked to phosphorus. It's very strong banding, and we cannot release oxygen from the structure. That's why phosphate are much more safe than oxide for application point of view. I will give you, as I promised, some example from R&D in our work. This is a recent work from SRUT in 2020. What we did is we select this Nazicon. It's a complicated formula, but we do some calculation. We do many experiments, and we choose this one. Okay, so we develop synthesis from phosphoric acid. It's very important because in literature we prepare phosphate mainly from salt, but here we have the challenge to use phosphoric acid. So this is a synthesis where we should control the pH. It's very important. So we succeeded to have a Nazicon type structure with good structural refinement, and we check the existence of carbon inside. Here is a comparison between the phosphate without coating and phosphate with coating, and we see that we have existence of carbon. TM shows that we have particle covered by carbon, which is what we need. And then we use this battery in half cell, and you see we have a good reversibility of charge and discharge process and good response at high rate. 5C is charging and discharging your battery in 12 minutes. But what we were surprised is by the long-term cycling, 1,000 cycles. Normally, in the scientific surrounding, in the lab, we need only 50 cycles to prove the concept. But here we go until 1,000 cycles, is almost the case of practical battery, industrial battery. So this opened the door of many, many phosphates existing in the Moroccan literature to just rethinking this material and to build a new good electrode material made from phosphate. Here, another one is this oxyphosphate, which is, you see, without lithium, is an anode materials. This is a work done by Hasna, who they funded last year. And you see, we prepare the same material. You see, we have some empty place here. We can put lithium, so our material can host lithium. He can play the role of anode. This is what we do. This is the discharge in blue. The first discharge, you see, we have a good plateau at very low voltage, anodic voltage. And you see we have a plateau and huge capacity, better than graphite that is used now in commercialized. But the problem is when we recharge the battery, we have a new profile. You see, we have some irreversibility. Normally, we should have a curve like this, but we have this irreversibility, and then we should understand why we have this irreversibility. So we do some operando synchrotron, and we see that during discharge, we have first crystallized material here with some peaks, but after that, we get amorphous material. So we have amorphization of our phosphate. This was surprising because normally phosphate are stable, crystallography stable, structurally stable. But here, by doing electrochemistry at room temperature, just to put in current, we completely destroyed the structure. And then what we do to be sure, because we have iron here, we use iron Mosbauer. So this is iron Mosbauer of the starting material. We have the doublet of iron triplets, but during discharge, you see we have this appearance of iron triplets and appearance of iron metallic. So iron metallic is going from the structure where is iron triplets to metallic, is extrusion, metallic extrusion of our phosphate. It was surprising, but it was possible by doing such experience. Now I have 10 minutes more, I think, or 5 or 10 minutes more. I would like to talk about sodium-ion battery. Why? Because sodium-ion batteries. You see that the cost of lithium is increasing since 2002 until now. Very, very huge increase of lithium. Okay, and lithium also exists in some politically unstable countries. Okay, but if we compare the cost of lithium carbonate, for example, here, and sodium carbonate, you see it's a huge difference in the cost. And also the salt, lithium PF6 and sodium PF6, you have like 3 times expensive. But from chemical point of view, we have sodium and lithium in the same place, in some row, column in the periodic table. And then normally we should have practically the same properties. Why we have this one? Because we have sodium more abundant in the earth. Is geopolitically dispersed, so we can have it from the ocean or from many places, and they have the same principle of lithium-ion battery. But as you will see, there are some problems. The first reflex, the first thinking, is to translate what we found from lithium since 1992 to sodium. So we replace cathode lithium metal oxide, for example. We replace it by sodium metal oxide in the cathode side. It works. We change the electrolyte from LiPF6 to sodium PF6. It works. But the problem was in the anode. Graphite doesn't work in sodium in batteries. So we should think about what kind of anode we should use in new concept of sodium-ion battery. But let me start by the cathode side. In lithium battery, we have this O3 structure. We have lithium and cobalt, during C-axis. And when we extract lithium or remove lithium, lithium is going from one octahedra to another via a triangular window. It's normal. It's lithium is very small. He can go there. But for sodium, which is bigger, we cannot have this diffusion easier. So the approach is now to prepare sodium oxide, sodium lyserge oxide, but with this structure where sodium is in prismatic side. Because if you have sodium in prismatic side, we can have this diffusion through rectangular window, square window here. So much more easier to have high diffusion and then high charge rate or fast charge or fast discharge. So what we do is directly to go to P2 type structure and to prepare new material NMC. And you see, we prepare by co-precipitation method, by using some conventional method in the lab. And you see here we have hexagonal-like plate. It's hexagonal symmetry. So in SEM, we saw we have really hexagonal particles that having around 1 to 2 micrometers. And you see here, we have our sodium in prismatic site, and we have AB sequence of oxygen. But the good news that when cycling our battery, you see we have really, really good reversibility doing charge, discharge. Okay, charge, discharge. Okay, this means that we succeeded to have this composition with a capacity of around 120 to 115 milliampere per gram, which is not so far. It's lower than lithium counterpart, but not so far. So we have this capacity, we have good efficiency, we have low cell polarization, and during in situ XRD, we show that P2 stay P2 during all stacking stable. So just a conclusion for this part, it's difficult to imagine that sodium-ion battery to replace lithium battery in electrical vehicles, because now the game is over for electrical vehicles. But we could think about technology of stationary storage, because stationary storage, storing renewable energy, we need huge quantity of material, and the cost is very, very important. And sodium materials, sodium-ion battery are very, very good alternative, low-cost alternative for storing energy. I know the materials. I have 5 minutes more.
2 or 3 minutes. 2 or 3 minutes. We have already passed the time.
Okay, I'm sorry. I'm sorry, because there are 2 things to say. Just I will present this anode materials. You know, graphite doesn't work for sodium-ion batteries. And we 3 or 4 years ago, during the PhD of Elias, we saw in the literature there are a lot of hard carbon prepared from biomass. And what we do, because in Morocco we produce a lot of data palm, we are the 8th position in the world, and we produce many stones, seeds of this essential fruits for our health. And what we do is to prepare hard carbon by some process, and this hard carbon was characterized by Raman, and you see we have this evolution of D and DG band, and we have amorphous hard carbon with some spacing between the layers coming much more wider. And during discharge in sodium-ion battery, you see here, we got very low voltage, around 0 volt, which is very, very important, and really huge capacity if we prepare it at 14 degrees Celsius. What we do is to use this hard carbon with phosphate to be close to the industrial cell condition. And the problem was how to equilibrate the capacity between the phosphate, we have this voltage, this capacity, and our hard carbon, and we succeeded to have this equilibrium, and we produce battery with 3.2 volt and around 700 watt hour per gram. It is really a best choice for storing solar energy. So there are a lot of new technology like lithium sulfur, lithium air, or redox flow, or the design will be also another challenge for lithium-ion battery, because we need to have some smart battery in the future to fix some problem that could be detected in the pack. This is very important, is the raw materials, because you see we have producing huge quantity of gadget, of electrical vehicles, but we will produce a lot of waste when the battery is over. So we will need a raw chemical material, cobalt, lithium, manganese, but also we will produce huge. And now people are trying to recycle this battery to produce high-value new chemicals. So let me conclude. I'm so sorry to be late. Just some reflection, you know. For the anode and cathode and electrode material, we have some actual technology. In the anode side, we have 3 million per gram. We use graphite, sometimes hard carbon, but in the future, we should have 6 million per gram to have phosphorus, silicon, antimony, use some additive or some additive for conductivity. For electrolyte, now we are 4 volt using some solvent, but we will use some, we'll need in the future 5 volt. So we should keep in mind that we should develop electrolyte, solid electrolyte, some fluoride additive, and some new solvent. In the cathode side, now the technology is from oxide, from spinel, from olivine. We have only 150 million per gram, and we need a technology that could reach twice 3 million per gram. So to do this, I have this flow. This is very important. So the aim is to have high power, high capacity, have time, safety, and cost. But to do that, we should think about new material or modify the existing material. Okay. We should also have some modeling before going to the experience. For that, we need some high power technique like in situ or ex situ, and we should think about environment issue and degradation of study. So by finishing, I would like to say something. So we should, you see that this topic is like a consortium between electrochemists, solid-state chemists, material science, design, and so on, electronics, and we should implement in Morocco some big consortium, and we should have some vision and strategy in the Morocco, what we should do in the next 10 years. And we should also respect the expertise. This is very important in Morocco. We have some overlap in between expertise we should have in mind. And think about the EV or energy storage ecosystem, especially for forming new PhD, new master student in this topic, which is now coming in the market, in the Moroccan roads. So thank you very much for your attention, and we have time for your question.
Thank you, Professor ISMAEL SAADOUNE, for your nice presentation. We have passed the time left for the presentation, but it was very nice that we have not read this presentation. Sorry for now we can give the talk to the Yes, Mohammed Al-Dawi.
Yes, thank you, Ismail, for a great presentation. Very well appreciated.
Thank you, Mohammed.
I enjoyed every minute of it. I just have one quick question. You didn't get a chance to go through it at the end. There is a big boost and big research going, especially in Asia, about sulfur lithium batteries. What can you say about that? And it seems like it's a good competition and it will avoid a lot of problems. Can you comment on that? And also, at the same time, advantage about what kind of research is going on in Morocco about improving the separators, which is also you showed at the beginning that's an important part of the batteries.
Yeah. Thank you, Mohammed. Thank you, Mohammed, for the nice question. In the last slide that I skipped, I had some comment on lithium sulfur. Of course, lithium sulfur we can store around 5 or 6 times than in lithium-ion battery, and this is really with lithium air the technology of future, I think. But the problem of this lithium sulfur is the shuttle problem, a big problem shuttle during the process of charge and discharge, and you have this sulfur is very unstable under air, and you should keep in some crucial condition. I'm not so specific, but what I know of for lithium sulfur, I think there are big challenge in the future to understand the mechanism of charge and discharge and to keep the process maintained during cycling. But from a practical point of view, from energy point of view, really is if we succeeded to have a good lithium sulfur, we can get autonomy for more than 1,000 kilometers or more than 3 days or 4 days for our laptop, I think.
Thank you, sir. How about the separators? Any research going on in Morocco about improving the separators?
Separator for lithium sulfur, for lithium batteries.
For the ones you are working on for lithium battery.
Yeah, lithium battery separator. Okay. In Morocco, I had the chance when applying for this proposal. I look what happened in Morocco, and unfortunately, there are not a lot of people working on lithium battery. We have our team in Marrakesh, we are team in UM6P, a team in Rabat, and in Masir, I think. But they are all working in the electrode material, cathode or anode. And no one are working on electrolyte, is electrochemist, and I'm asking Sibyl Khairu, who is a specialist in electrochemistry. This is a good topic. Separator, now I know that there are some polymers, some people working on that in UM6P, but they are not obvious research work. I didn't saw in the literature some recent work on that, but I think this is some topics that should be implemented in Moroccan universities, I think.
I just want to make one quick comment, if you allow me.
Yeah, Mohammed.
Chairman, I have to congratulate ISMAEL for his research in the last 20 years or so. It is not easy to do research, especially a long time ago, 20 years ago, and ISMAEL was always very productive, publishing high quality papers. I may make sure to congratulate you on that. That's double congratulations. Well done and keep going. The outstanding work, ISMAEL.
Merci. Shukran, Mohammed. Merci beaucoup. Merci.
Someone else for a question? Ahmed Al-Nawi? Professor Ahmed Al-Nawi? We don't hear you. Your micro, Professor. You have question, Professor Nawi?
You can read his questions in the chat. Actually, put them until he fixed his microphone, maybe.
Yeah.
Now we hear you. We hear you.
Now
yeah. I can see that Hamnawi said that lithium-ion battery modeling based on big data. Yeah. Unfortunately, there are 3 questions. Your comment on the topic: improve product quality and to ensure product stability of lithium-ion through a small side battery which higher. Your comment on the topic. Yeah, improve product. Yeah. To be humble, in Morocco we don't have any facilities to produce huge quantity of electrode material instead of materials. So what we do now is just producing some grams, maximum 1 kilo from materials, and even you prepare this huge quantity of material to go to the process to produce electrodes. No one has this in Africa, I think. No one has this facility to produce big modules with the material pasted in some current collector. So no one can do this in Morocco now. And I think, in my opinion, we should not waste the time to do that. Now the battery technology and electrochemical technology is in advanced position. If you start now, it will be too late. We can continue to work to produce electrode, battery, and so on. But we should think about new type of material. This is a first idea. Secondly, we should prepare our students, our master students, to how to react with common batteries, common electrical vehicles, because if you use this technology with less attention, you can get some fire. You saw that we saw many problems. So we should prepare our country, our young people, how to manage this battery, how did it work, how to optimize the things. I think this is my opinion. Big data, of course, if you would like to do modeling, you should have a big computer, big data, and so on. I think in my slide design that I skip also very fastly, we should have some self-healing. We should put some sensors in the cell and the pack in the module, so we can check. We can have some language between the driver or the producer and the battery inside, because you have not only one cell, sometimes we have 1,000 cells. And if you like to change one cell, you cannot change whole the pack. You should have some sensor inside, and just to short circuit, if you have some cell that doesn't work, you can keep it out to store your pack. And for that, big data, intelligence artificial should be a good approach. Now I know that many PhD theses in Europe are focusing in some optics inside the cells, putting some sensors and optics in the cells. This is my answer to Ahmed.
Yes. The last question is, have you some? Where are you with the phosphate for batteries? Are you in the beginning?
Okay. Okay. Phosphate is very wide research topic. In Moroccan library, you will find a lot of phosphate, nazik and glasses and so on. But if you see, there are only some structure, some Raman infrared spectroscopy, and that's all. What we are trying in one thing is how to make alive, faire survivre some such phosphate, and to show that we can store a lot of lithium or sodium in this big structure of phosphate. This is what we are doing, is like fundamental but applied research. LFP is the biggest one. LFP is the more commercialized, but the problem is LFP is already done. What we are trying to do is how to prepare LFP from such critical condition using some phosphoric acid or some special additive. We can do it, but the problem, I think, is the way the Hydro-Quebec and now some Chinese are very good in the technology preparing LFP. Now we should think about some alternative. We produce also fluor. We can use some fluorophosphate, but this means that we should start now, and we should start not like one R&D lab in Marrakesh, but like one biggest consortium, and to see all the aspects of phosphate, not only material science, but also modeling and electrochemical.
Okay, thank you. Thank you very much.
Thank you. Another question? Yes, Professor Touzani.
Yes, thank you so much, Professor SAADOUNE, for this nice presentation. I have two questions.
Mm-hmm.
The first one, you spoke about lithium and sodium. What about potassium?
Mm-hmm.
Do you have any idea about potassium?
Yeah.
The second one is you advise that to get very good batteries, you use large particles. What about nanomaterials? Because the first conference with Professor Nawi, he said that the smallest you go, the smallest you be efficient. And thanks a lot.
Thank you very much, Tuzani. First of all, for the potassium, now in the labs, in the research labs, there are a lot of technologies. There are potassium-ion batteries, calcium-ion batteries, because in calcium-ion batteries we have 2 electrons. So you double the capacity. You have aluminum-ion batteries and magnesium. This is all technology, I think, is in the initiation process. Yeah, 2-3 years. Potassium ion batteries, there are a lot of work done in Japan. I know that. And what I was surprised, because what I see is graphite worked with lithium. Yeah. But for sodium, it doesn't work. And at that time, we think about the sum of sodium. But surprisingly, graphite worked for potassium, for very well. So now there are a lot of work on potassium ion batteries. So this is the answer for the first question. For the second question, yes, this is a huge people are now would like to work on nanotechnology, nanomaterials. Of course, having nanomaterials that could shorten the lithium diffusion, that you could have some fast conduction, fast charging, discharging. But the problem of nanoparticle, of small particle, is that you have high specific surface. This means that we will have high reactivity with the electrolyte. and you will have some side reaction between electrolyte and your material, which will provoke the apparition of some SEA, solid electrolyte interface, that will inhibit the lithium diffusion and so on. Second problem is it appears that during the processing, during the pasting of your material on the collector in the industrial part, research, it's very difficult to pass particle with low size, nanoparticle size, than bigger particle like micro, submicro.
Thanks a lot.
May I ask one short question?
Please.
Yeah.
So this is Dual from Spain. So thank you so much, Ismael. It's a really very nice talk and huge data. And as you said, it's a pity that you published it before patenting. Yeah. So please next time patent first and publish later. Yeah.
But I'm too old now. I'm so old. It's too late for me.
Yeah, but we are doing a lot of job now, a lot of things. I see that you published it just this year, last year. So I hope that you patented all these works before publishing them. Anyway, I have just a very short question. You know, it's very simple. So what about the nature of the solvent of you're using in the cell? I mean, because you have diffusion, as I said many times at the time and so on. That depends on many things like viscosity, like interaction with this and this and this and so on. You know this. Could you tell something, please, about that?
Yeah, thank you very much. Yes, the electrolyte now used in the cell is a salt, lithium phosphor LiP6, dissolved in ethylene carbonate or propylene carbonate or sometimes dimethyl carbonate. Is generally carbonate because they are of the viscosity, of the stability, and so on. But all these solvents are stable under 4 volt, 4.2 volt, 4 volt. If you go higher in voltage, it doesn't work. You should put some additive, some organic element that stabilize the structure. But we should keep in mind that we should have some good ionic conductivity and good viscosity to be used in real batteries.
Yeah, just as far as you know, from disolar cell, so the last generation, I mean, that means about 10 years ago, but since 10 years ago, disolar cell have stopped, the field because of perovskite. But I mean, at that time, many people use ionic leakages, for electrolyte.
Yeah.
So is there any I don't know, any challenge in this to go in this direction for
you are right. I think I showed something in my slide when talking about electrolyte. There are a lot of people now also working on ionic liquid, but the problem of that is their cost. They are a little bit expensive compared to what we have from normal solvent, normal electrolyte.
Thank you so much. Yeah, very nice work, and I hope I will meet soon. Yeah, maybe in Marrakesh. Yeah, so I have to go there to visit my friends and old site. Yeah, thank you so much. Shukran jazilan. Shukran.
Please. Please,
Professor Hamouti.
Yes. First, thank you so much, Professor SAADOUNE, for this very interesting conference, and congrats from several colleagues from Facebook, and someone, Mustafa Abdullawi, asked about if we can replace lithium ion by hydrogen ion.
No. If there are some fuel cell. Fuel cell, we are using hydrogen as energy carrier. No problem. For that, it's very competitive. Is now in the industry, hydrogen. But proton ion, this means that you will have some ionic solvent, some aqueous solvent, and you know that water is stable only in the window of 1.2 volt to 1.4 volt. So you will get very low. If it works, it will give you a low energy density. Now we are looking for higher voltage, like 5 volt. And if you use some aqueous, you will generate some oxygen and hydrogen inside the electrolyte, I think.
Okay. Yes. In other words, if you mind to to have lattice where lithium ion is free for free diffusion to reach cathode or anode.
I didn't understand the question. I'm sorry.
In other words, we have to prepare some solid state where the diffusion is free for lithium ions to reach cathode or anode.
Yeah, and if I understand the question, yes. Now you have an anode material, electrolyte, and cathode. This is the cell. So you should have lithium diffusion in the anode fast, in the interface between anode and electrolyte fast. Inside the electrolyte should be fast also and safe, and between the electrolyte and the cathode interface. So now people are trying to prepare some solid electrolyte, polymer or solid like garnet or phosphate. But the problem is this interface between the solid interface. This is the big challenge, is we have to prepare some interface to make easier the transfer from one side to other side of the component of the cell. This is the big challenge. If we succeed to have that, I think Volkswagen succeeded. We can get 5 volt, more than 5 volt battery, and this means that you can drive for a long time without any problem, because we will have some higher energy density inside.
There is some question. Another question.
Yes, I am pleased to inform you that about the number of viewing this conference. It reached more than 5,000.
5,000?
Yes.
Oh, this is good.
5,128 qui sont touchés.
Oh, thank you. It's good news.
Very good.
Yes, very
Excellent.
good. Thanks to our manager in computer, Mr. Zarhi Abdelhaq, who sent me now this information.
Thank you. Donc جبت الموديل ياك كتب الخير. فاليديت الموديل. جي فاليدي الموديل.
Oui, الله يعطيك الصحة ولا يطول عمرك. Thanks, of course. On a fait beaucoup de publicité, donc c'est sûr. Toutes les conférences, all conferences reached some thousands for many groups in the Moroccan university and outside of Morocco.
Thank you. Thank you. Thank you very much.
Yes, and Turkish also.
Oh, great. تشكرات لكم. Okay.
I have a question. Why clays are not used in these batteries for lithium?
Sorry?
Clays.
Clays?
Yes.
As electrode?
Yes.
Okay. One of the requirements of electrode is to have some molar mass, very low molar mass.
Mm-hmm.
And clays, you have inside a lot of silicate, yes. Carbonate, and so on. So the molar mass is very huge. So you will get a few milliampere per gram if you use as electrode material, I think. Okay. And secondly, also, to the best of my knowledge, we don't have a good view on the real composition of the clays. The purity and the reproducibility of the process is very important with such technology.
Yes, there are some synthetic clays like laponites. They are good crystals, and they give good gels.
Okay, it can be used as a separator, for example.
Yes.
No problem.
Another question. If we had nanomaterials like bag, and we make some lithium, can we use this like a cathode?
I'm sorry.
Can we use nano capsules, like bag, with lithium as cathode.
Nano capsules, yeah.
Yes, nano capsules.
I didn't. I didn't saw.
Atoms of lithium.
I didn't saw before such a capsule in lithium-ion batteries, but I think we should have.
Technologically, it can be done technologically.
Yeah. Everything is possible, but we should think about one thing. If you insert lithium in some capsule or whatever, we should think about reversibility of the process.
Yes.
Because we have charge and discharge, and if you have some encapsulation of lithium, it will be not good stickability of your lithium-ion battery, and you should have only a primary battery, just one discharge and it's over.
Yes. Okay. Thank you.
You're welcome.
Any questions?
تحية سي سعدون. فيه مراسل للجزيرة يطلب الهاتف الشخصي ديالك سي إسماعيل سعدون.
مرحبا، عندك التليفون سي بالخير؟ نو
والله ما لقيتوش البارح عندي.
انا غادي نصيفط لك بار واتساب ولا شي حاجه.
والله صيفطوا لي السي الناوي حفظه الله واطال عمره.
انا جميعا انا غنصيفط لك حتى تسويت بغيتي مورا الكونفيرونس.
ثانك يو سو ماتش.
ويلكم. ياك ولا نصيفطوا سي فواز ياك حتى هو سي بون.
معنا نعم.
داكور ميرسي واخا.
Now we thank all peoples and all scientists at this session, and we thank Professor SAADOUNE for this presentation, and now we will close this session.
Thank you very much.
Thank you very much at all. Yes.
Thank you all. اسبيرون ان شاء الله الافاي يمشي عندنا ونتلاقاو في ظروف احسن ان شاء الله. فيفو. ميرسي بوكو. تحياتي وتحياتي الناس ديال وجده.
بعد هذا الويبينار راه كيجمع واحد المجموعه ديال العلماء حفظهم الله اللي اختارتهم ديك ستانفورد يونيفرسيتي بارمي 2%.
لا مرحبا مبروك عليك صاحبي.
ورستي كيقول واحد المجموعه ديال لي كوليك حفظهم الله.
شكرا للجميع. ميرسي بوكو.
Merci.
الله يعاونكم ويكم.
Thank you.
ويكند ان شاء الله. نسوغون دونك حمدي عنده شي حاجه.
مونداي.
ان شاء الله.
السلام. شكرا. مع السلامه. السلام.
السلام عليكم.
عليكم السلام.
السلام عليكم.
عليكم السلام. Have a great day, all of you guys.
ايوا الحمد لله حفظكم الله ورعاكم. شكرا الاخوه والله يطول عمركم. شكرا جزيلا للسي بوكلاح على لي سيسيون. السي عبد الحق الزرعي الله يطول عمرك. السي الحسين البودوتي عنده جوج ديال لي كونت تبارك الله عليك. بعدا الدبل ريشارج بعدا كاين لي باتري شارجمون. سي توزاني. السي الحسين الورغي. عاشت الحسيمه لاله الصالحي الله يحفظك. وبعدا غير مره في الحقيقه هذه غير مره نتلاقاو على الميت غير نبتسم في وجوه احبابنا وابتسامتك في وجه اخيك صدقه. يلا تبارك الله عليكم.
حفظ الله الجميع.
الله يبارك فيكم. هذه فرصه ان شاء الله باش نفوتوا واحد الويكاند زوينه. الحمد لله راه كاين